Here is a sample first exam of Linear Control Systems class. I found this class to be very difficult and time consuming. Here are the questions I will be going over. I did not finish question 4 or the extra credit question. This is problem number 1 of the Control Systems Exam 1. So the first one, we got to draw the signal flow graph of this diagram. So what I like to do is number the nodes. So we got 1 for the input, 2 for the first summer. We got 3, this one is the third node. This is the fourth node is the second summer. The fifth node is the third summer. And we got 6 as the output. And we'll start drawing the signal flow graph. We got 6 nodes. So we'll draw these out. And I like to go ahead and label them. Got R of S input. Call the first summer E1. We'll call this node just 3. We got the second summer here, the third summer, and this is Y of S, the output. Okay, we'll go ahead and connect this one forward path. And let's see, we got the other path splits off at node 3 and goes to node 5. We'll go ahead and draw that in. And that one had the gain there at that loop, or that top path, is G1. Then we got, this is the gain between the input and the first summer is just 1. We got G2 between the first summer and node 3. We got, let's see, between the third node and the second summer is just 1. And between the second summer and the third summer, we got G3. And we just got 1 between the 5th node and the 6th node is 1. Okay, now we got 2 loops, 2 feedback loops. We got 1 between the 6th node and the 4th node. And keep in mind, that is positive. Very important to note that. So go ahead and connect that 6 to 4. And again, that is positive H1. And the other feedback loop is going to the first summer. That is negative feedback. So that's negative H2. Okay, part A is done. That is the signal flow graph. So let's go ahead and we're going to use that to work on part B. For this part, we got to use Mason's rule. So our transfer function of the closed loop transfer function in the S domain is going to be equal to a summation between 1 and the number of paths. The summation of the gains of the forward paths, which is TK, and delta K, and over delta. Here the delta K's are going to be equal to 1, so delta 1 is equal to delta 2 is equal to 1. And let's first, we want to find the gains of the forward paths. We have two forward paths. We'll have this path 1. It's going to go across and up and over. And then path 2 is just straight across. Path 1 is equal to 1 times G2 times G1 times 1 is equal to just G1, G2. Path 2, straight across, we just got 1 G2 G3 times 1. So we just got G2 and G3. Next up, we just gotta find the delta. And delta here is just going to be 1 minus the loops. Loop 1, loop gains, loop 3. So we have 3 loops here. Okay, loop 1 we'll use this as the smallest loop right here. Is loop 1. So here we got G3 times 1, which I won't have to put down, times H1. That's loop 1. Loop 3, just going to go cross over, back around to its starting point. So loop 2. I might have said loop 3. We got G2 times G1 times 1 times negative H2. And that's just going to be negative G1 G2 H2. Okay, and now the last loop. Last loop is just going to start in the same spot the last one did. We're going to go across and down. And that one is going to be loop 3. That's going to be G2 times 1 times G3 times 1 times negative H2. This is simply negative G2 G3 H2. Okay, and now we've got it. So delta is equal to 1 minus G3 H1 minus G1 G2 minus G2 G3 H2. We'll go ahead and distribute the negative. The final answer is going to be equal to summation of the loop gains times 1. So we got G1 G2 times 1 plus G2 G3 times 1 over 1 minus G3 H1 plus G1 G2 H2. plus G2, G3, and H2. And that is the answer. This question. Now, for number 2, we need to find A, B, C, and D matrices using the state space variables given right there. First thing we want to do is explain the system's equations with those variables. Analyzing the circuit, you can see that the voltage across all of these components are going to be the same because they both share the same node. We got ground, and the voltage here is all going to be the same. So we got the voltage across R of T is equal to the voltage across the inductor, which is equal to the voltage across the cap. We use KCL to write an equation for the currents through the components. So we got U of T, the current source, is equal to the sum of the currents through the components. So next, let's write the equations for the dynamics of the inductor and the capacitor. With the inductor, we got the voltage is equal to L di of L t dt, and the current across the capacitor is equal to the capacitance times dV dt. We gotta isolate each derivative. First, we'll start with the inductor. So di L of t dt is equal to 1 over L Vc bt, because the voltage across the inductor is the same as the voltage across the capacitor. That is equation number 1 that we're going to use to find the state matrices. For the next equation, we have to isolate the dV dt. We use our equation for the currents. IR of t is equal to Vc of t over R plus the current across the inductor plus the current across the capacitor, which is C dV C t dt. Now we'll isolate dV dt. Now that we have found the derivatives of the state variables, we can start to write the state differential equation. We have to put the equations in the state differential equation form. Q dot of t is equal to A qt plus B u of t. Solving for di dt in the first row of A is going to be 1 over L times Vc of t. So I of L is not in the equation, so we'll put a 0 in the first row, first column, and 1 over L in the second column of the first row. And solving for dV dt, we see that we have a component of -1 over c IL of t, so that will go here to be multiplied by IL, the current across the inductor, and we have -1 over RC times VC of t, so that will go in the second row, second column. And we have the input being multiplied by 1 over c, but because there is no input component in the derivative of the current through the inductor, the first row is 0, and we have it in the dV/dt, so we're going to put that in the second row here, which is going to be 1 over c. Okay, we have found A and we have found B. Those are taken care of. Now we can find C and D in the output. Output vector is equal to VC of t and IR of t, so that's written as where VC of t is just equal to VC of t, and IR of t is equal to VC of t over R. Therefore, the output, which needs to be written in the similar form of C times the state variables and D times the input, will be equal to V of C is equal to V of C. Because there is no IL component, we have a 0 times IL, and we just have 1 times VC. That takes care of the Y1 of t. Y2 of t, we have IR of t equal to VC over R, VC of t over R. So there is no IL component, so we have 0 there, and we have 1 over R times VC of t. And because there is no input in either equation, we have zeros on the input for D. Therefore, for question number 3, we have to find the transfer function using the Laplace transform for the given differential equation. For A, we're just going to factor out the y of t and the u of t on both sides and replace the derivatives with s. The transfer function will be y of s over u of s. Okay, for part B, we are going to have to draw the phase variable format block diagram. The degree of the denominator is 3, so we know we're going to need 3 integrator blocks. We are going to have a summer at the end and beginning. 5 times the S2 component. That's going to be negative feedback. We have 10 times S. We have a gain of 8 by itself, so we're going to have to add in that gain block before the summer on the end. For the gains up top, we got 4 coming from S. We have 2 coming from S squared. We have the output. And we are done with part B. Just wanted to go over point out the nodes, just so it's clear. This node is S cubed. We have S squared, S, and that is our final answer for part B. For part C, there is just a simple procedural method to converting the transfer function to the state variable description to find the matrices of A, B, C, and D. First, we're going to multiply the numerator and the denominator of the transfer function by s to the negative 3 over s to the negative 3. The transfer function will now be in this form. The matrices of A, B, and C now follow this form. Finally, we'll just plug the values from the transfer function into this form. Therefore, the final answer is where your matrices are here. And that's question 3 fully answered. For number 4, part A, delta S is equal to the determinant of S times an identity matrix minus A. And you set that equal to 0 to find the characteristic equation. For part B, the state transition matrix in the S domain is equal to Si minus A, that quantity to the negative 1, which is equal to 1 over the characteristic equation times Si minus A. Now that you have the state transition matrix in the S domain, we have to put it in the time domain using inverse Laplace. In order to do that, we're going to have to use partial fraction expansion and then use the Laplace transform, inverse Laplace and Laplace transform table, which you should memorize. Now that we've used partial fraction expansion, we are able to use what we know from the Laplace table to find the final answer for part B. The two inverse Laplace transform forms that we want to look at is this one that we should know. It's that one and this one. So following that table, our final answer will be this. I noticed one little mistake, so I have to backtrack just a little. And that should be correct. The transition matrix is the matrix exponential function that describes the unforced response of the system. And that concludes part B of question 4.